We propose a data reduction pipeline for steady vector field data using deep learning techniques. Our approach consists of low-resolution initialization and high-resolution refinement. Our approach can evaluate the quality representative streamline selection algorithm. In addition, we also compare our approach against gradient vector flow and lossy compression.
Uncovering causal relations in event sequences can benefit decision-making in various applications. We present an interactive visual analytic system, Sequazzle. It incorporates an algorithm with a user feedback mechanism for learning causality in event sequences under the supervision of human experts. It also provides a set of visualizations to support causal exploration, verification, and comparison.
Comparative layout are the visualization arrangement to support visual comparison tasks. To better understand them, we conducted a systemic survey on 127 research papers. Based on the survey, we suggest a lucid classification as well as diverse practical implications that help you better design comparative visualizations. Find out more in our presentation.
We present the visualizations for the RAID-C AD simulation ensemble available on the VIS Contest 2020 website to analyze the commonalities and differences in the AD features observed across the ensemble members. Specifically, we demonstrate the applications of statistical visualization techniques in the context of volume rendering, mass complexes, and isocontours to gain insight into the potential AD positions and their spatial uncertainty for the ensemble.
Urban traffic congestion has become an important problem. Previous studies have focused on detecting traffic congestion and predicting future trends. However, it is difficult to find research that identifies the causes of traffic congestion. In this paper, we propose a technique to analyze the cause of traffic congestion based on the traffic flow theory.
Many real-world analysis environments involve multiple types of experts and analysts working together. We aim to provide new knowledge about the role of provenance in a variety of data analysis scenarios. We present the findings from interviews with the data analysts from various domains. Our results demonstrate how different needs for provenance depend on different analyst roles and also helps to identify possible opportunities for advancements and new techniques for provenance support.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
In visual analytics tools, provenance is used to capture activities on different levels of granularity. However, current approaches do not support inferring tasks spanning across these levels. We propose a framework for inferring user tasks from provenance involving 3 stages: initializing, parsing, and leveraging. We will present a use case to show the roles of context, variability, and iterative refinement. Join us further discussing our agenda and the challenges of implementing such a framework.
Dimensionality reduction is an important tool for the visual exploration of complex high-dimensional data. Most existing techniques focus on preserving the intrinsic geometry of the data during the projection. However, important informations can be encoded within the global structure of the data. To address this, we present TopoMap, a dimensionality reduction method that provably preserves the topological features of the data during the projection.
MetroSets is an online platform for visualizing sets as metro maps. In this style of drawing, sets are represented with metro lines, while the elements they contain are represented as stations. MetroSets is implemented using a modular 4-step pipeline with a variety of choices for each step. The final visualization is interactive with support for all common set operations. MetroSets is fully implemented and can be found at the displayed URL.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds.
Hello, I'd like to welcome you to a little gala that we've put together to highlight the state of Utah, the University of Utah, and the Ski Institute. You know, when we were originally planning the VIS event, we wanted to highlight one of the unique features of Utah, and that was our Natural History Museum, which is part of our University of Utah campus, and highlight one of the unique features that we have here in our state, which is actual dinosaur bones. Now, unfortunately, because we're not holding this physically here in Salt Lake City, we had to come up with something else to do for you. And so we have coupled with the Natural History Museum, and in particular, the director there, Jason Cryan, and he's going to give you a tour of the museum.
Hi, my name is Jason Cryan. I'm the director of the Natural History Museum of Utah, and I would like to welcome you to this fantastic museum. Before we go explore the inside of this museum, take a look at the outside of the building. This museum is clad in copper mined locally from the Kennecott mine. It's nestled right up against the Wasatch Mountains and has a beautiful view of the Salt Lake Valley. Come, let's explore. As we come up the stairs into the museum proper, you'll be greeted with the sight of our beautiful atrium called the Canyon. This room has a commanding view over the Salt Lake Valley, and also you notice that the walls are irregularly shaped. And that's because they've been scientifically modeled after the mountains just behind the museum building. Your first stop in the journey through the museum today is this relief map of the state of Utah. With this map, we invite you to come and see where you live, where you've been, and where you would like to go in this great state of Utah. Before we explore the museum exhibits, I wanted to point out our collections wall. Most people don't realize that at our core, this museum is based on research and collections. We have more than 1.6 million specimens in our collections, most of which the public will never see. They're held for research purposes. This wall has 600 of them that we use as examples of all of the breadth of biodiversity, of geological diversity that we hold in these collections. We have an app called the Trailhead to Utah, which gives you all kinds of information about this museum. Let's listen to what my colleagues have to say about this collections wall.
The collections wall is designed as a work of art, and it's meant to show how extraordinarily beautiful nature can be.
What makes our institution special is our collections. It's our heart and soul. It's at our core.
Butterflies with fossils, fossils with plants, historic pots.
The baskets represent extreme work and labor.
Insects are pink and chrome color and black and brown and fuzzy and striped and polka dotted, and they're more beautiful than jewels.
Thanks very much for joining us today. You're in for an exciting visit. We can't wait to meet you in person on your next visit to the museum.
Welcome to the Past Worlds exhibit of the Natural History Museum of Utah, where we explore over 150 million years of Utah's ancient past. Today, the Great Salt Lake is a fantastic place to see living dinosaurs, all those birds flying above us. And though the shorelines are teeming with life, in the water there's not much else besides brine shrimp. But about 12,000 years ago, it was a very different matter here in Utah. The Great Salt Lake was much larger, a big body of fresh water called Lake Bonneville. And it not only had all sorts of fish living in it, but all sorts of other animals along its lake shores, including things like mammoths and mastodons and saber-toothed cats. And in the Wasatch Mountains, we had glaciers. So it was a very different world, even though it was just a few thousand years ago. Further back in time, some 50 million years ago during the Eocene, much of Utah and Wyoming was covered in large freshwater lakes. These lakes were teeming with life, with all sorts of birds, as well as mammals, including this early relative of humans, Notharctus, on this branch. There were also strange microbial structures called stromatolites, which we also find in the Great Salt Lake today. Now we're back 75 million years ago during the Cretaceous period. And you can see that all the different animals around back then were quite different. We have large meat-eating tyrannosaurs like Teratophonius behind me, large alligators like Deinosuchus, and the environment was quite different too. We had broad, slow-moving streams and rivers crisscrossing Utah that would have looked similar to what we see in southern Louisiana today. We're finally back 150 million years ago during the late Jurassic period, when Utah was covered with an open savanna-like environment that had a few large rivers and streams. And walking on this landscape were all sorts of classic dinosaurs, like Utah's state fossil Allosaurus, and the giant long-necked plant-eating sauropod dinosaurs like Barosaurus. This is sort of the iconic dinosaurian landscape, and it shows how much Utah has changed over the past 150 million years. Extinctions have always occurred over the history of life on Earth, but 66 million years ago, at the end of the Cretaceous period, we had one of the 5 largest mass extinction events on record. Utah during this time was teeming with dinosaurs like Tyrannosaurus rex, Torosaurus, and Triceratops, but they all went extinct in a geologic instant. An asteroid hit the Yucatan Peninsula of Mexico and not only vaporized a ton of rock, but caused instant climate change. And this is what we think caused the extinction of the dinosaurs. Just a few million years after the end Cretaceous mass extinction event, Utah was a very different place. There were all sorts of mammals roaming around on land, including small early horses. And in the lakes, we see all sorts of fish and reptiles that look similar to modern animals that we see today. During the Pleistocene here in Utah, there were all sorts of amazing animals such as saber-toothed cats, cave bears, mammoths and mastodons, and giant ground sloths. But by about 12,000 years ago, they were all extinct. So why did all these large mammals go extinct at the end of the Pleistocene? Well, we know things were getting a bit warmer and a little more humid. But also, we have the arrival of humans here in the Great Basin and other parts of North America, and humans are great at hunting large mammals. This is a time that we call the Pleistocene megafaunal extinctions, and at least here in North America and Utah, we think humans played a role in these large animals like mammoths and mastodons going extinct.
There's something about DinoFest that just captures people's imaginations.
To bring in speakers from all over the world that are experts, that provides a unique opportunity to the public.
It's good for people, I think, to see scientists that look like them, who are excited about what they do.
Festivals like this are one of the best ways you can actually both educate and reach out to the public. It makes a big difference when kids are able to come behind the scenes and see the process of science and collections that are taking place.
Hello everyone, welcome to the Natural History Museum. Normally you see the fossils that we prepare on the other side of the window, but to really get into it, I need to bring you into the lab today. What I'm doing today is I'm working on this dinosaur specimen to get this ready for research or display. To get this specimen to the lab so that we can work on it, first we have to collect it, and by collecting it, we'll wrap it in wet paper towels and then plaster and burlap to protect the fossils so that we can bring them back to the museum to work on. You may ask why we leave so much rock on the specimen, and that's to protect the bones, because if we take too much rock off in the field, it's really easy to damage or fracture parts of the bones, and when we remove the rock, we want to do it in the controlled environment of the lab. Now, it'll probably take this specimen at least 6 months to a year before you see it on display in the museum or before researchers can start their work on it. So one cool thing that we find as we prepare fossils a lot of times is we find anomalies on the bones. So this is a rib of one of our Tyrannosaur specimens, and as we prepared it, we found this weird little halo of bone in the center of this rib. And what that actually is where the rib broke and then healed during the life of this Tyrannosaur. And as we prepared more of the ribs, we found several more of these breaks. So that one point in this animal's life, he broke 8 ribs and they all healed back together. A question I get all the time is, how do I distinguish what is actually fossil bone and what is the rock around? So one of the ways that we can do that is if we get a specimen wet, sometimes there will be a slight color change between the bone and the rock. So in this case, the bone is this nice chocolate brown, whereas the rock is this kind of salt and pepper gray. But in the field, sometimes we don't know. So one of the ways that we tell if something is a fossil or rock is you'll see paleontologists all the time in the field licking the fossil. And the reason that we lick it is there's still microscopic holes in the bone, and the bone will actually stick to your tongue, where fossilized rock and fossilized wood will not. So that's a trick that we can use to determine if something is bone or rock. Once we're in the lab, we use a plethora of tools to start removing all this rock away from the bones. So we'll use this tool here called an air scribe. So it's like a miniature jackhammer that slowly chips the rock away. And then when we get close to the bone, we use the same tools that you would see in a dentist's office. We use lots of dental picks to slowly chip away the little grains of sand around the bones. We'll also use lots of chemicals, basically like super glue, to glue all the bones together and keep them together while we prepare the specimen till we can get it on display.
Let's talk about fossilization. What is a fossil? Generally defined, a fossil is evidence of past life that has been chemically or geologically altered. There are many different ways a fossil can form, so let's look at some of those. One of the most common ways that a fossil is formed is by the process called permineralization. So let's take a theoretical dinosaur, like this Griposaurus skull here. You have this animal that at some point died, and the soft tissue rots and decays away. The skeleton and the bones are then buried. Over time, more depositional events, more sediment is laid on top. So you have layer after layer of mud or sand. These turn to rock and encase that bone within the rock. Therefore, the bones are now under a lot of heat and a lot of pressure, and they're also subject to something else within rock, groundwater. Groundwater moves through the crystals in rock, and they bring dissolved materials with them, dissolved minerals, and that does two things to bone. It can bring minerals into bone, and it can leach minerals out of bone. So in a bone, just like ours or any dinosaur or any vertebrate animal, you have cavities. What that means is these cavities can be the spots where these dissolved minerals actually collect and recrystallize and actually turn what was once entirely bone into a fossil, which is part bone and part rock. Some other ways that fossils can be formed are via a process that we call replacement, and that is where you have, again, a theoretical dinosaur bone, and instead of it being permineralized, being partially still bone material, all that bone is actually leached away by that acting force groundwater that we talked of. And again, that same material, that groundwater, has dissolved minerals in it. It comes into this empty cavity where bone once was, which is now just an empty space, brings in those minerals that were dissolved recrystallize, and they turn into an exact copy, cast, or mold of that original dinosaur fossil. And occasionally, in all of these different methods of fossilization, we see varying degrees of recrystallization. Sometimes that doesn't affect a fossil much, sometimes that affects it a little bit more than we see in others. Trace fossils are a kind of fossil that's not a body part, but it's evidence of animal life. We see an example of that right here with this skin imprint from the duck-billed dinosaur Griposaurus. The animal died, fell over into the mud, slaps down here, the skin rots away, the mud hardens, and then more wet mud fills in. Now, when these have turned to rock, we can split them apart. We take the other side, we have an exact replica of what this dinosaur's skin felt like. Some other trace fossils you may be familiar with are trackways. Maybe a dinosaur or other animal is walking along a lakeshore, and this mud or sand then hardens into rock, and then we can find them and study them as paleontologists. It might be little scurry marks of a trilobite from deep at the bottom of the ocean. Another kind of trace fossil are actually dinosaur droppings in other animals. There are even vomit fossils. There are all kinds of different remains from animals that are actually left as traces, and then we can study those too, and that gives us additional information about how these animals, dinosaurs and others, lived their lives.
Well, now you've seen the Natural History Museum. We want to show you one of the museums that you might have wanted to go to that's downtown. This is a museum that's dedicated to innovation and creativity, combining that with technology. It's called the Leonardo. So we'll show you some clips from there. So we mentioned in the opening that the host institution is the University of Utah. And like we said earlier, we were hoping that we would be able to get you up on our campus. But we've put together some footage in combination with our marketing team so that you can get a small sense of what the University of Utah campus is like.
No, we are not the standoffish scientists that everybody thinks we are. We are often known by the acronym SCI, which stands for Scientific Computing and Imaging. We are the Scientific Computing and Imaging Institute. We're a research institute that really researches the cutting edge, brings the top caliber people in visualization, in image analysis, and in scientific computing to work together to solve problems that none of those individual expertise could solve by themselves.
You know, it's hard to believe, but this will be the third time that the SCI Institute has been the host of IEEE VIS here in Salt Lake City. The first time was in 2000, and then once again in 2010, and now in 2020. I've been the interim director of the SCI Institute since Chris Johnson, the founding director of SCI, stepped down in 2018. It's been a real honor to try to lead SCI through this time, and I'd like to announce that the new SCI director has been chosen. Manish Parashar from Rutgers University is the new director of SCI, and he will be joining us on January 1 of 2021. I know that he's excited about continuing SCI's traditions around scientific and data computing, imaging, and visualization, and I'm confident that the SCI Institute will continue to be a leader on the VIS front.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Ensuring the usability of a dataset is often tied to data wrangling. We can use provenance to log the